Hey folks, Cool18 here, and welcome to another Unity tutorial on how to make a 2D game called ClonyBird, obviously a clone of the very popular Flappy Bird game. So we've got our bird graphic in there, we've got our background, which is great. Now what we're going to do is add some basic sort of controls to our bird. Our actual bird script is going to be extremely simple. Sometimes what I might do is make multiple scripts, one to create control the movement of objects and another one to deal with player inputs that then feed the movement script and all that. But our game here is so simple, we can easily make do with a single script. So I'm going to go ahead and do that. And we're going to create a new script. We're going to call it bird movement. That's going to be, plenty good. We're going to just call it that. It'll be a C# script because that's just what I prefer to work in Unity. I'm actually a very big fan of JavaScript in general, but not so much in Unity, partially because the JavaScript in Unity is sort of kind of not real JavaScript, and also just because C# I feel just ends up being a lot stronger. So how does our bird work? Again, going back to how the actual Flappy Bird kind of thing works, it generally, if you don't do anything, gravity will grab onto it and pull it downwards. It also tends to tilt slightly. If we double click on there, as gravity starts to pull this downwards, it will also tilt downwards until it actually faces straight down, at which point it will be moving quite quickly. So let's naively make some assumptions about how our bird works. We're going to give it, it's going to have a velocity. Let's go, oops, that was weird, vector 3 velocity. Right, which by default, of course, is going to start at vector.0. I don't have to put this in, but just let's remind ourselves it's going to start at 0. Okay, and then every frame, now, because this handles movement, ideally you're going to want to do this on a fixed update. Every frame, gravity is going to be applied to this object. Well, now here's a big question. Since we're using things like gravity, and obviously we're going to want to, say, collide onto the ground, would we like to use the physics system? Right? The Unity 2D has a built-in 2D physics system. It's an interesting question. And I don't know if Flappy Bird would more appropriately use the built-in physics system, or if we're just going to fake it. I think what we're going to do here is fake it, just so we have slightly more control over the speed of things. In fact, what I'm going to do is I'm going to set up a public vector 3 called gravity. And we're going to have it set to, well, we'll just leave it like that, and that way we can set it in the editor. So every frame on fixed update, which is where the physicsy kind of stuff should happen, we are going to take our velocity, and we're going to add gravity. Okay, let's start with this. Let me tab out. Actually, wait, hold on. Let's not start with this. And then we're going to go into transform.position, and we're going to move ourselves by our velocity, and of course, times time.delta time. Right, so this is velocity is the amount of distance you're going to move in 1 second, but this update was going to be run multiple times per second, so we want to know how much time has gone by since the last time this was called, and so just multiply velocity like that. So generally speaking, it'll be like velocity times 0.02, I think, because I think by default fixed update will run about 50 times a second. All right, so that should, if we take a look at our player bird, and add a negative y component. Now, actual gravity is negative 9.8 meters per second squared. All right, let's try this and just see what happens to happen. Wow, it falls way too fast. Of course, because we're quite zoomed in, right? Things are not going to be very physicsy. That's obviously much too intense. It's possible that I've made some other mistake here. Let's see. Let's put something quite small. Let's do something like this. All right, that might not actually be too bad. Obviously falls much slower than an actual physicsy object. Oh, that's way too fast. No, we want to go down quite low. Does that, oh, I'm being foolish. I'm adding the full gravity every single frame instead of the amount of time that's gone by. I do that every time. So now it's going to go way too slow. Good, okay. So let's go back to negative 9.8 meters per second squared. Okay. I think this is physically realistic, but I think it's way too fast for the game. And so let's go like -4. Let's try that. All right, that might be okay. We can play with different options and see how that goes. But we'll say -4 is relatively reasonable. Okay, so that is number one. The second thing we want to do is compute whether we have flapped this frame. Now, I'm actually a fan of splitting the inputs and the outputs. The reason is, okay, so we're going to try to see if the keyboard was pushed this frame. The problem is, if I open up the stats here and I hit play, let's see what our FPS looks like. Okay, it looks like right now, because of our graphic settings, we are currently doing Vsync. Yeah. So what does Vsync mean? This means it will only draw basically once per monitor refresh. It won't draw faster than your monitor refresh rate. And the real reason for that is, one, there's kind of no reason to ever draw faster than your monitor refresh rate because you won't see it. The other problem is that the actual V-synchronization is that sometimes halfway through your monitor refresh rate, the game might actually update its own frame view. So halfway through your monitor refreshing itself, you're suddenly going to start seeing another frame, and it results in something called frame tearing. This was more of a problem back in the bad old days, but for the sake of argument here, I'm actually going to disable the Vsync and hit play again, and this will give us a true frame rate right now. So we're running at, well, it was hundreds of frames per second at first while the graphic was there, and then once that graphic is gone off screen, it's thousands of frames per second. So let me explain why that's a problem. Let's put the Vsync back on. The reason that's a problem is because fixed update only runs once every 50th of a second, which is not really every frame. So if you do something like check if input dot get key down, this is the question of, did the key go down this frame? Then return true. The problem is that you could miss a frame where this was true because fixed update doesn't necessarily match up with the actual frame rate of your computer. And I believe that this is based on your actual frame. It's cleared on every visual frame. So what we want to do is in void update is where we want to deal with the inputs. I don't think I'm lying to you in this case. It's possible that I'm mistaken. Do check the comments down below, and certainly if you know something else, let me know here. But I'm pretty sure that's the way it is. And certainly in general, this is correct. Fixed update, this is where you do graphic and input updates here. Do physics engine updates here. And because this might run slightly slower, you rely on your CPU slightly less often to do physics calculations. And also, internally, if your computer is so slow that you're not doing visual frame rate updates consistently enough, it can skip some frame rate updates to make sure that the physics stay accurate. While you might actually get 2 or 3 of these physics updates between graphical frames, all kinds of different things. It's probably not important for our particular example, but what the hell. So let's set up a Boolean here called did flap, which defaults to false. So if input.get key down, and frankly, it's like there's not an any key, is there? Like that would be, like, I don't know if they have an any key thing in Unity, because that's actually what we want. But for the sake of argument, let's say that keycode.space. You can use the space bar or input.get mouse button down, and we're going to put in 0, which is the left mouse button. Also, if you're playing on a mobile device, taps anywhere on the screen respond as a get mouse button down of 0. It's like a left mouse click. So clicking the mouse, tapping the screen, or hitting space on the keyboard, this will all return true. In which case what we'll do is we'll set did flap to be equal to true. Then over here in our physics engine, so we've added the gravity. If did flap is true, right? I'll make it explicit. If it's equal to true. This is more typing than is necessary, but if it's equal to true, then first thing, set it to false. We're going to reset it. Then velocity is going to be equal to what? To our actual like up and down kind of velocity. So what is it? We're gonna create a public vector 3. This is gonna be called like flap velocity. So what we're gonna do is our velocity is we're gonna add our flap velocity to our velocity. It's gonna be a one-shot thing, and then we're gonna set the false. That I think this should work. Let's find out. Let's go back to our bird. So what we're going to have to do is give it some sort of flat velocity. And it's going to have to be relatively strong, I think. Maybe like 1 second worth of counter gravity. And we're not doing a time dot down till time here. We're just going to instantly give it a boost of velocity. So I'll hit play. Oh, that's actually pretty good. Every time I hit space. All right, I see one problem here because we are adding velocity, which is actually let me going a little too high. If I hit it multiple times. Well, first of all, there's no cooldown, which is certainly a problem. But I think what we're also going to want to do is instead of adding this flap velocity, I think we're just going to want to set our Y to our flap velocity. That's one possibility. The other thing we could do is cap it to a maximum vertical velocity. I'm not sure if it makes a difference. All right, let's set velocity.y to be equal to flap velocity.y. Yeah, but what if we want flapping to also change our forward speed? All right, let's set public float max speed, there we go, is going to be equal to, let's say 5. So after we add some velocity from either gravity or from our flapping, but before we add it to a position, we're going to make sure that our velocity is equal to vector3.clamp magnitude, velocity, and max speed. So this will ensure that our velocity cannot exceed our max speed. Going up, going down, going forward, going left, all those things put together cannot exceed that. And that will probably make a more reasonable game. Now, obviously, we're going to want a ceiling. I think our speeds are probably a little too high on like kind of every side. Let's have the gravity, have the flap velocity, and our max speed, we could keep the same. Oh, I think that's better. Again, I'm not comparing to the actual game. I could have both things side by side and see how they feel. But let's play around with this right now. Now, the other thing you'll notice is my bird is constantly flapping. Also, and I specified that in Flappy Bird, when your bird is falling, he will rotate to face downwards. That we can do. We can do that pretty easily, actually. So what does rotating to face downward look like? If we mess around with this, that's not the one I want. Z-axis. There we go. If we mess around with this, if we're at minus 90 is kind of what we're looking to do. At minus 90, we is facing downwards, and of course at 0 is facing forward, which is normal. So in fixed update, we can potentially do that, although is that a fixed update or is it a graphics update? Well, it's going to be based on our velocity. As our velocity approaches the maximum downwards velocity, then we're going to want to face more and more down. Okay, that's pretty easy to do, actually. So let's figure this out. I guess we want to do a lerp. Okay, float angle equals mathf.lerp. Wait, is a lerp angle? I actually don't know what lerp angle is for. It probably automatically deals with 360 degree issues. Let's just go with a normal lerp. We're going to want to lerp from 0 to negative 90 as, so the third parameter here, t, is a 0 to 1. If we enter a 0, it's going to use the first parameter, which is 0. If we enter a 1, it's going to go to minus 90. If we go 0.5 like that, then it's going to go halfway, so it'll be 45 degrees. So this is as our velocity. What? Velocity dot y divided by, hold on, I'm not doing this right. Divided by max speed. So assuming it was still 5 here, what is this going to do? If our velocity is exactly 0, and our max speed is 5, so this will return 0. If it's positive, it'll give me a positive number. If velocity is under 0. Let's only do this code if it's under 0. Do stuff. I hate when the autocomplete is not doing what I want. Actually, let's set our float angle, our angle here, to be equal to 0, and just override it. So, if the velocity is under 0, we're going to change what our angle is. Normally, it's just going to stay as 0, and what we're going to do is set our transform dot rotation equals quaternion dot Euler. It's got no x-axis rotation, no y-axis rotation, and our z-axis rotation is going to be this angle that we feed in here. So now we just have to make sure that we get this right. So if the velocity is 0 or above, it's never going to do anything. So this will always be a negative. So let's set a negative here divided by max speed. So if it is basically 0, if we're basically going level, so it's still going to return 0, which is going to return close to this. And then as we approach max speed, so as we get from, again, assuming max speed here is 5, which is not because we've messed with it, but if it were 5, so as this approaches 5, then it will approach 1. So because 5 divided by 5 will be 1. Normally the y will be negative here, so we're just inverting this, so it'll reach 1, it'll return closer to minus 90, and put in there, I think that will basically do what we're looking for. Let's go and see. Hey, there we are. Okay, the flap is not quite sending us vertical. Oh, and I know why that is. It's because we're just adding the flap velocity. So we actually want to set the flap velocity to, well, like almost anything, like 999. We just want to cap it out. When we flap, we want to go up as fast as our max speed allows us to be. Except 3 is too high. Do we want to do it that way? I'll set it to 4, so it's at least enough to overcome the maximum negative speed. No, that's way too much. Maybe before we flap? Now there's an idea. Let's set the flap velocity to only 1. But before we flap, if velocity.y is less than 0, then set velocity.y to be equal to 0. First cancel any downward motion and then add some flap velocity. So that way we'll never be going down after a flap. And then we can still flap more to go up. Oh, that feels pretty good. That kind of feels like the way you would expect it to work. Okay, I like it. Obviously, we still have to set a ceiling to the game, but that's feeling pretty decent, visually speaking. Now, of course, we don't have any left to right motion. Now, in this game, the left to right motion is basically fixed. Vector 3, fixed velocity. Whoops. Actually, I guess I'm just rename this to a float, actually. Float forward speed. And we'll set it to 1F by default there. I'm feeling better about that. So after we add the gravity, I'm also going to set the velocity dot x to be equal to our forward speed. Actually, I'll do that first, just for the sake of argument. Yeah, so our forward speed is generally speaking going to be fixed. Technically, we could sort of kind of mess with it with these x's, but right now we won't. We might change the way this code works, but for now, we've got a fixed forward speed, except that I have an error. Let me open the console up just so that I've got a little bit more room over here. Oh, really? Just complains about an extra semicolon? Huh, how about that? Learn something new every day. There we go. So now we've got a fixed forward motion. Now, obviously, we have a bit of an issue in that our camera, our game camera, does not move with a bird. So we should do something about that. What do we want to do about it? Well, there's a few different things. First, and potentially the easiest thing to do, is you would... okay, here's the obvious thing. Let's put the main camera as the child of player bird and see why that doesn't work. Doesn't work because, oh, right, the bird rotates, and as we go up and down, weird things happen. That's not good. So plan A is no good. What we want is a script that sets the main camera's X to keep pace with the bird's X. Now, we don't want the camera to actually be centered on the bird. We actually will always want the bird to be... What am I moving? I'm moving the bird. Move the camera. We want the bird to always be sort of close to the left edge of the screen. Not right at the left edge of the screen, but pretty damn close to the left edge of the screen. So I think what we're going to want to do is let's set the player bird to have the tag player. And then the main camera, we're going to call something like camera tracks player. We're going to create a new script called that. Okay, and these types of scripts you get written all the time in these kinds of games, especially anything side-scrollery, and it just comes down to a big question of exactly what is the camera supposed to do. In this case, and the code is going to be, let's grab the transform of the player. Transform player in the start, player equals game object dot find by name, actually find object with tag player, which actually returns a game object, but we are interested in the game object's transform. Now, this could actually fail, so let's break it down a little bit and do things kind of righter this time. Game object, we're going to call this player game object is equal to this. If player dot game or player game object is equal to null, then what we need to do is debug.log error. Couldn't find an object with tag player. And then we're instantly like freak out, like just let's break out of the start thing, but nothing in your program is going to work right if this happens. So obviously we got to throw up an error right away. And then assuming that this doesn't happen, then we are going to set our actual player object to, so we've got the game object, but what we want is the transform, because the transform contains the information about the player's location, and that's the thing we actually care about. So the other thing we're going to do is we're going to set the camera initially to the right, the correct left-right offset. Because you can see here, if we set the, so the player, let's set the player to like x equal to 0. It's not necessarily ideal. I know, let's start off at 10 again, just to make sure that, oh, not 10. Was it 4? Where's the bird? Right over there. Yeah, that works out pretty well. And move it there. Actually, no. We will set the player to 0. And the camera, we're going to pull back. So ideally, this is the sort of thing we want. We want the player to be just a little off the left edge of the screen. And then we'll adjust the background to make sure it doesn't go over. I mean, hell, I can take this whole background and sort of shift it over this way just to make sure that everything is totally groovy. Okay. And we want to keep it there. So as the bird moves forward towards the right, we want to keep the camera having this space. Now, part of the problem is originally we don't know how to set the space correctly because it's going to depend on the aspect ratio. If I change the aspect ratio, you can see that because the size changes, it's not good. So what we actually want to do on start is we want the camera to be aware of what the width of the screen is, what the position of the player is, and offset itself by the correct amount at that point. So let's figure this out. So let's assume everything is starting off at 0. There we go. The bird is at 0. The camera is at 0. That's great. So we want what? What do we want? Let me think here. All right, the camera. We need We need to be able to convert world coordinates to camera coordinates, or screen coordinates to world coordinates. That's what we want to do. We want to say, okay, we're going to know the size of the screen, and we do know that because we've got screen dot width available to us. We know the width of the screen. And so we want a space, I don't know how many pixels from the left-hand side of the screen. That'll probably be fixed. Maybe like 50 pixels from the left-hand side of the screen is where we want the bird to sit. Now, depending on the size of the screen, you're going to have more or less warning. So no matter what, your bird's going to be sitting kind of like this. Actually, I suppose I could do it as a percentage-based thing. We'll mess around with a few different things, okay? So we want some sort of fixed space there, and then, yeah, depending on the size of the screen, you're going to have more or less warning about what's coming up in front of you. Actually, I'm going to keep saying all these things. What I could do is pick, like, one of the narrowest aspects, set the camera to something workable for that, something like this, and then when you've got a wider aspect, you've just got a little bit more gap afterwards. That might be way, way, way simpler. And visually stronger. Shoot, I think I may have just talked myself into doing something like that instead. The programming would be much, much simpler. Let's go with this. Here's the number one thing with programming. Just make it work at all, and then figure out how to make it work better later on if it's not working for you. All right, so we're going to go with that kind of idea. So eyeballing it, actually that seems to work pretty good. Hopefully it works at every resolution. Again, here it would break if we moved into a vertical mode, but we actually don't want to run the game in this because it would be effectively unplayable. And actually, I guess the like degenerate case would be something like a fixed ratio, a square ratio. Something like that. Still fits there, so this is the degenerate case. Anything else would be wider than this, so we know for a fact it's going to work. Hey, I like it. Okay, good. So we've got that. We've got the player object, and so what we want to do is figure out what our current offset is. What do I mean? Offset X. We know where the player is. We know where we are, so our offset is simply the player dot position dot X. Actually, it's... Yeah, it's ourselves, transform.position.x minus the player's position, and every frame, and that's our offset. And then every frame, we want to set our transform.position.x to be equal to the player.position.x plus offset x. I think I'm getting the math the right way around here. We also actually need to check if player not equals null, because the player could die. Or something like that. We may decide to delete the player at some point, in which case we are no longer want to do any math with it. So if the player's still around, then we're going to want to make sure to offset ourselves based on the player. And assuming I didn't invert my math like I very frequently do, and make an error here. Oh, right, I forgot I can't write directly to this X as is. You can do this if you're working in JavaScript, but otherwise what you have to do is vector3 pos equals my position, and then set the positions X, and then set transform.position equals pos. You can't write to the dot X of this directly. You've got to set it to a new vector3. Again, in JavaScript, it'll work. Hey, there we go. Yeah, we're correctly tracking the bird and keeping it in our view. Oh, that's wonderful. Actually seems to work pretty damn well, honestly. Which I'm kind of vaguely surprised about, but I'll take it. So, obviously the background is still not scrolling. We probably want to work on that next, because the code we're going to use is also going to be used for our obstacles. So, next thing we're going to do is make sure that our background loops with us. See you next time, folks. Bye-bye.